speaker. She is Alessandra Stella from Jülich Forschungszentrum, and now we switch really from math to a statistical problem, and she will speak about surrogate techniques for testing higher order correlations in parallel spike trains. Please, Alessandra.
Thank you. Can you see the slides and can you hear me well?
Yes, we do.
Okay, thank you. I just moved the Zoom panel. Perfect. So thank you, Laura, for introducing me. Thank you for inviting me. Yes, I work at Jülich Forschungszentrum at the Institute of Neuroscience and Medicine in Germany. And this is joint work done together with Peter Booth, which is another PhD colleague of mine, Professor Gunther Palm and Professor Sonja Grun. So the title is already quite clear. The context is pretty much different from the previous talk. But I hope that it will be anyways interesting for you. What I'm going to present is starting from the context. The background is the Hebbian assembly hypothesis. So Donald Hebb theorized in 1949 that assemblies of coactive neurons act as information processing units. With Hebbian assemblies, we are talking about groups of neurons that are co-activated time after time and in different space within the brain. This is theorized. There are already some experimental evidences, but context and different backgrounds can be very, 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 very different. So our more precise hypothesis is that the assembly membership is expressed by precise temporal coordination activity in the range of a few milliseconds. So typically speaking, this is what also is called in different words as temporal coding. This is not an easy hypothesis. Actually, it is pretty much different and complicated to test it statistically. There are different approaches to test higher order correlations or pairwise correlations in spiking activities of parallel spike trains. So again, we are in the context of parallel point processes, but more an applied approach. There are different approaches. Again, some of them start already quite classically from a cross-correlation analysis, a cross-correlation histogram, which is a quite old, but again, very used approach that looks at pairwise correlation in time. There are more advanced approaches that look at the dynamics of correlations, just as the joint pair stimulus time histogram. There are approaches that look at higher order correlations, so starting from triplets of spikes detected across trials, such as the unitary event analysis formulated by Sonja Grun, but also the spatial temporal spike pattern analysis formulated by Moshe Abeles. There are already quite some experimental evidences of significant triplets in cortex, in macaque motor cortex, in a paper by Riley et al. In Science in 2006, or in Prut et al. In 1998, which again are results already that are becoming old. And then there are more advanced and recent approaches that look at higher order correlations. So starting from correlation of size order 2 on, so triplets or quadruplets of spikes. Here I listed some of them. There are many, many more, but the ones that I'm going to concentrate about are this one and this one. So maybe I should explain a little bit more because this already looks quite a large topic, what actually we are more interested in within this project. Actually, our hypothesis in terms of the Hebbian assembly hypothesis and the temporal coding is that assembly activity is expressed by the occurrence of precise spatial temporal spike patterns with precise temporal delays between the spikes emitted by neurons that are presumably member of an Hebbian assembly. So the structures that we are looking for in the data look more like this. They can be synchronous patterns of spikes coming from neurons that always belong to such patterns. It can be synchronous, they can be delayed, as you can see here. Of course, the red dots represent the patterns. But we can extend what we are going to talk about also to propagation of synchronies that you can instead see in panel E, which can be considered basically representations of a fire chain activity. So when we want to look at this and we want to test for it, we might think of assuming a model behind it. Maybe a simple point process model like a Poisson process, and trying to estimate how many times would such a pattern occur, fixing the number of neurons and so on, and maybe an average firing rate. But unfortunately, we have to look at the reality of experimental recordings if we want to analyze them. And the reality is not so easy. So we can see from many studies done in the past that experimental data has complex features, that a complete and satisfactory analytical approach is often very hard, if not possible. And for instance, this is well represented in this paper, Mochizuki et al. Published in 2016, where they grouped together different data sets analyzed by many labs. Actually, the number of authors in this paper is quite impressive, looking still at macaque, so fixing a species, macaque cortex, but varying, actually not only cortex, but varying the area of the brain. So in this paper, they looked at the statistics that are seen in the motor cortex, in the prefrontal cortex, and the hippocampus. And they looked at their general statistics across different experiments, you can imagine. And they see that the firing rates strongly change in time. They are non-stationary in many ways. The firing rates change also across trials. The firing rate onsets or offsets change across trials, so like latency variability. And they also see that spike trains pretty much deviate from Poisson. So from the Poisson assumption, actually we can see that in more motor cortex, the data look more more regular than a Poisson assumption. We can, so these are interspike interval distributions. Sorry, I should have mentioned it. Less in the prefrontal cortex. Instead, in the hippocampus, data looks instead more bursty. So all of these evidence serial correlations. And this is actually why when we want to test for higher order correlations, often the case is that a model is not assumed actually, but different approaches need to be used. For example, one might decide to generate surrogates. So, and then we come to the title of the talk. Surrogates are a very classical way of generating a null hypothesis when a complex analytical description is not possible or very hard, and it consists in manipulating the data, for instance, destroying the feature that we want to test for. In this case, it's the potential fine temporal correlation, extracting one measure from the original data and from the surrogates, generating, of course, many surrogates, a large number of them, in order to derive a distribution of such measures that needs to be compared to the empirical measure that is observed in the original data. And then from the surrogates, of course, we need something to derive a significance. It can be the surprise, it can be a p-value, and so on. This is often used in general, for instance, already from a cross-correlation study that you can see here. This is a cross-correlation histogram, a cross-correlogram. There's a time lag between the central spike on the x-axis and the count on the y-axis. And what we can actually see already from earlier studies is that we can get obviously different results depending on the surrogate technique that we decide to use. So it is actually worth, before looking at our test, to vary and to choose a proper surrogate in order to derive significance. And this is what we tried to do for higher order correlations. So here I present you 6 different surrogate techniques that we decided to look at. here you need to be a little bit concentrated, although the techniques are very easy, but they are 6. So I'm going to go through one by one. The first one is a classical approach. It is called uniform dithering. Remember that we want to generate surrogates from continuous time spike trains. Uniform dithering consists in the displacement of each single spike according to a uniform distribution of a parameter that is usually in the range of a few milliseconds for temporal coding, and it has been used in many studies. Again, this is the classical approach that does not take into account the biological characteristics of experimental spike trains. So one might decide to incorporate some of those biological characteristics and extend this method. We decided to, on our own, to extend the classical uniform dithering by just incorporating the dead time. The dead time, that is the refractory, biologically speaking, the refractory period of the neuron. It is hard to estimate also mathematically, but it can be enforced sometimes by the spike sorting algorithm. And basically, this adapted approach consists in displacing each spike by uniform distribution, but still keeping a time constraint between successive spikes such that the dead time is not violated. Our next approach that is more advanced is what is called the joint interspike interval dithering, which was designed by George Genstein in 2004. And this technique displaces spikes according to the joint interspike interval distribution of adjacent interspike intervals. So adjacent means one after the other. So we have the first interspike interval on the x-axis, the second interspike interval on the y-axis. We sample all these interspike intervals from our original spike trains, and then we use this distribution to sample surrogates. So this has the nice characteristic that it preserves many statistics, such as the interspike interval and the joint interspike interval distribution. But of course, we need enough spikes to estimate such a distribution. So this is a quite advanced approach that can be simplified by also looking only at the interspike interval distribution. So taking into account how we sample the joint interspike interval distribution, we can just replace this distribution with the outer product of the ISI distribution. So just sampling based on the interspike interval distribution, not keeping the joint, but still the approach is quite similar to the previous. And it also leads to good results. We will see it afterwards. The next approach is also, again, quite easy. It's called trial shifting. It consists in, instead of shifting each single spike, in shifting the entire spike train. This is particularly powerful if we have data that is segmentable, meaning that we have a standard experiment where we have trials. The animal is doing trial after trial. So we shift each trial, single trial, and each neuron independently by a uniform distribution. This has the nice characteristic that it preserves mostly all statistical features, of course, because the spike train is just shifted. And then finally, the last approach is a discretized approach. So meaning that very often when we want to look at and evaluate correlations in continuous time spike trains, we often do it on the discretized version of the process. So the discrete process, like a 0-1 process. So we might think in this context of just shuffling locally the bins, the bin contents, so shuffling the spikes within a window that can be a tiny window, given that we are testing for temporal coding, so we want to keep the firing rate profile preserved, and it's also algorithmically simple. So again, I presented all 6 of them. They're already over. And maybe I want to say why we want to use them. So of course, we want to detect, as I said before, spatial temporal spike patterns in parallel spike trains, but I haven't said how we do this. So there's a technique that we have developed over the years that we call SPADE. It stands for spatial temporal pattern detection and evaluation, and is able to find such structures in parallel spike trains. So these are 2 patterns, actually 1 pattern occurring 2 times across these 4 neurons over and over and identically. SPADE combines an optimized mining technique that is called frequent item set mining that looks for patterns in spiking data, and then tests such patterns for significance, obviously using surrogates. So maybe a little bit in a detail exactly how SPADE works. I can show in this figure. So spiking data is given as input. It's subjected to discretization and then mining of such patterns with the mining technique that I was saying to you before. Patterns are collected, and then since we don't want to test each single pattern because they are evidently many in such large data sets that we tend to analyze, we decide to group them due to their statistics. So basically we group at patterns depending on their characteristics, of their order of correlation, and on their temporal duration. And then we do the same thing on the surrogates, of course. We collect all these statistics, collect them in a p-value spectrum, basically evaluating in how many of the surrogate datasets we find patterns that were detected in the original data. We divide by the number of surrogates, we correct for multiple testing, and then we get a p-value that we use for testing. After a second conditional test on the patterns that I don't want to talk about, we get significant patterns in return. So what I want to show also in this figure is that we can use different surrogate methods. And actually what we want to show is that we get different results, and why it is important to use a proper surrogate methods for such estimation. So why did we decide to do this? The classical technique, the uniform dithering that I was explaining to you before, already gives some problems when applied to experimental data. Basically, we saw that the application of uniform dithering, again, it's the temporal displacement of each single spike locally, applied on experimental spike trains, if the data are discretized, which is often done, leads to a reduction in the spike count. Not only this, which is already quite troublesome for statistics in general, but also that many of the intrinsic characteristics of the original spike train are disrupted. For instance, the interspike interval becomes more exponentially distributed. The dead time is not preserved. The regularity of the experimental neuron is not preserved. And all these effects get stronger with increasing firing rate, which is often the case in the motor cortex, which is the area that we are interested in. So when we found this, we decided to investigate further which are the reasons for this. And I can show you very briefly as a sketch what happens in practically. Basically, if the original spike train has a dead time, some sort of regularity, for instance, intrinsic regularity of the spike train, firing regularity estimated with the coefficient of variation, or simply a dead time, it can happen that by moving uniformly this spike, actually all spikes, it might happen that they end up in the same interval that it used for the discretization. And thus, this leads to a reduction in the spike count. If you see here, we have 8 spikes that we end up, obviously here, it's, we want to give the idea, we end up having only 4. So we decided to model this analytically, so a little bit of math, by using 2 spike train models. The first one is a Poisson process with dead time that was introduced by Deger et al. In 2012, and by a gamma process. We decided to derive analytically the spike count reduction in function of the firing rate for the original spike train and its surrogates. This can be done quite easily, actually, from the distribution, the interspike interval distribution of these 2 processes by varying the dead time and the gamma parameter of the gamma distribution, and by looking at the surrogates here dotted and the original spike trains, we see that there's a mismatch in the spike count. And the consequence of this is quite dramatic, because when we try to model this by looking at distributions of patterns found in ground truth data, meaning different realizations of processes, and by looking at their corresponding surrogates, we see that there's a shift and the p-value distribution, meaning that there's an overestimation of significance that leads to false positive detection. Obviously, we do not want to detect false positives, so we need some alternative techniques to the uniform dithering. This is actually why we introduced this alternative 5s, and it gave us the opportunity to see what happens when to look at the statistics of the surrogate techniques when we vary the surrogates algorithm. So first, we started looking at homogeneous data, stationary data, 3 simple models: the Poisson model, the Poisson process with dead time, and a gamma model. We studied some of the statistics by varying the surrogate techniques, for instance, the spike count, the interspike interval, autocorrelation, surrogate independence, and so on. This figure is, I admit, quite complicated, so I want to give you an easier interpretation by looking at a table that shows basically which of these characteristics, which of these statistics are kept and which are not preserved by each different surrogate technique. So as we can see right from the beginning is that uniform dithering does not preserve many of these statistics, which are important for us as we are testing for, again, temporal coding. So the more characteristics of the original spike plane preserved, the better for robustness of any test. But we can also see is that different techniques preserve different statistics. And there's in particular one winning technique, which is the trial shifting here, that in the case of homogeneous data preserves most of these statistics, basically just by definition. So this is already quite nice result and is quite satisfactory. Of course, the problem is that, again, as I said from the beginning, we were only looking at stationary data, which is not applicable to experimental recordings. So we decided to actually generate data that are non-stationary, and we decided to model 2 sessions of an experimental data set published in 2018 in the laboratory of Thomas Brochet in Marseille, with these 2-point process models, the Poisson process with dead time and the gamma process. We estimated the non-stationary firing rates neuron by neuron, trial by trial, very finely. We estimated the coefficient of variations and turned it into a parameter of the gamma process, and we estimated the dead time for each single neuron in order to have data sets that look like experimental data but are otherwise independent. So if we look for spatial temporal patterns in independent data, we should find few false positives, of course. Some of them need to be there because it's a statistical test, but we don't want to find many. And what we see when we apply SPADE across different surrogate techniques is that uniform dithering leads to a large number of false positives. And this is obviously not good, whereas the other surrogate techniques almost give the same number of false positives, beside uniform dithering with dead time, which is not really great for gamma process. So more false positives are actually more detected for the Poisson process with dead time when the intrinsic irregularity of the neuron is not included in the model. Furthermore, we looked at the characteristics of the neurons involved in false positives. Mainly, we found that neurons that have a firing rate higher than 20 Hertz and the coefficient of variation lower than 1, actually CV2 because the data are non-stationary, tend to be more involved in false positives, whereas very regular neurons, neurons with low firing rate, and neurons that are bursty are not involved in false positives. So taking into consideration all these results, we can identify that pretty much all these surrogate techniques are good for us. But of course, given the results on stationary data, we might prefer the trial shifting for our purposes. And finally, I want to give you a short glimpse of an application of experimental data that is quite interesting. So again, it is the same data set that I was referring to before. It is an experiment done again in Marseille in the lab of Thomas Brochier. There is a 10 by 10 Utah array electrode implanted in the pre and motor cortex of 2 macaque monkeys that are doing a reaching and grasping task. Basically, they are pulling an object that you can see here with 2 different grips. And we want to detect spatial temporal patterns that are locked to the behavior of the monkey. So we segment the data accordingly, and we are able to look at these 2 different monkeys, 2 different sessions on different days, and vary the surrogate technique. Of course, here we do not have a ground truth, so we are not able to see whether these are false positives or not. But what we see is that, again, uniform dithering leads to a large number of patterns detected that, due to the results that we obtained before, we tend to discard as putative false positives. Whereas we find many patterns by using the different surrogate techniques that I showed you before. And actually, we find more patterns than, of course, false positives, which is very nice. Actually, almost double or triple the number. And these patterns are very similar across surrogate techniques, lead to basically the same significance threshold, and overlap in their neuronal participation. So basically, they are the same patterns, which gives us a very nice conclusion in terms of robustness of our findings. My time is over, so I conclude. We hypothesize that the assembly activity, Hebbian assembly activity, is expressed by spatial temporal spike patterns in parallel recordings that are emitted by neurons that are presumably member of such an assembly. So to detect such patterns, we have developed a method that does so and took into consideration 6 different surrogate techniques. We see that the classical surrogate technique that is often used together with spike train discretization leads to a strong spike count reduction in the surrogates. So we decide to study the statistics of these alternative techniques analytically and through simulations. And we see that when applied to non-stationary data, uniform dithering leads to a large number of false positives. And concluding, one of the methods that we propose, trial shifting, is our preferential method for the evaluation of the significance of patterns in parallel spike trains. I thank you all for listening. I thank my group of statistical neuroscience in ULISH and my supervisor, Professor Sonia Grun. Thank you so much for the patience.
Thank you for the presentation. Are there questions or comments? Write on the chat if you don't have the possibility of switch on your microphone. If no one has comments, I want just to give a small comment. You will say that the uniform dithering is moves the distribution toward the exponential behavior. And
yes.
This looks to me very natural, because somehow uniform dithering is a way to delete any form of memory in your spike train, and the exponential behavior is the zero memory instance. So I think that any type of dithering will somehow try to destroy this the different behavior of the tails.
Yes. So unless you specifically design a technique, for instance, as George Genstein did back then, to preserve the interspike interval distribution, pretty much any interspike interval structure is disrupted, which is, yeah, obviously a problem. Of course, if you want to preserve it too much,
you don't get information.
You don't get information back. Yes.
Yes. Yes, it's true. Sure. Any further comment? No. Otherwise, we thank again Alessandra.
Thank you.
And we switch to the next speaker.